Two identically charged 1 kilogram spheres are on a horizontal frictionless surface as shown below. One ball is attached to a string and the normal force on that ball is 8 newtons. Determine the charge magnitude on each ball and the tension in the string. Now, as always, I'm going to solve this problem, but it's going to be different, at least in some ways, as compared to any other problem that you are going to be working on. So what you need to focus on is the approach that I'm using. That's what you want to focus on and try to apply to your problem or problems. Now, in this case, it's asking me for the tension, which of course is a force. So my first inclination is to try Newton's second law, which means I'm going to draw a force diagram. So I know I've got gravity, and I know I've got the normal force, which is pointing straight up. Because my contact surface is horizontal, the normal force has to be perpendicular to the contact surface, and it's a push force. I've also got tension, of course, so that's going to be like this, roughly like that. That's not perfect. It should be parallel to that string, but that's close enough. And my two spheres are identically charged. That means they have the same polarity, which means they are repelling each other. So that means I've got an electrostatic force going to the left. Okay, so now I'm going to set up Newton's second law. Let's start with the horizontal forces. So remember that this means I'm doing the sum of the forces in the x. So my x components, and of course that has to equal ma. I have no acceleration here, so it's going to be equal to 0. So what are my x forces? Well, I've got ftx, and I've got fex, and that's going to have to equal 0. And I should have had a little x there for the acceleration. Okay, now in this case, I know that I'm going to call to the right positive. So I know that since the electrostatic force is an axis vector, I can write this as minus F sub E. There we go. And I can go ahead, since I know I'm looking for the charge magnitude on each one, I can put in the formula for the electrostatic force, but I'm going to leave it right there. That's good enough for right now. We'll come back to it. Now for the y, so I've got, let's see, F in y plus F ty plus F gy all has to equal 0. And let's see, this is going to be just Fn because, again, Fn is an axis vector. I've got another axis vector, and I called up positive. This is plus Fty. This is going to be minus Fg. Okay, now I know the mass, and hopefully everyone remembers that we know how to calculate weight. That's Fg equals mg. Okay, and I know the normal force, so I can easily solve for Fty here. It's going to be Fg minus Fn. Okay, so that's going to be, since Fg is mg, let me go ahead and do this up here. This is 1 times 9.8, and that's, of course, just 9.8. So Fg is 9.8. My normal force is 8. And I'm going to do a little vector analysis here for my Fty. Okay. The y component, so if I am interested in this angle, I'll use this angle here. I'm going to call that theta. Okay. So that means that didn't mean to say F. I meant to say, that means if I want let's do the cosine of theta. Cosine is adjacent over the hypotenuse. Okay. And that's also going to equal, so the adjacent side, you can see here for this triangle, the adjacent side is vertical, and if I do my little vector diagram here for the ft, this vertical side here, this is fty, this is ftx, okay? This angle here is of course theta, just like I have there. So that means that what I'm going to have for my adjacent side is fty over ft. Okay, and I know the adjacent and the hypotenuse. The adjacent is 4. That's for this side here. My hypotenuse is 5. And what that means is if I just solve for fty, it means I'm getting 0.8 times ft equals fty. And it may not have been clear when I was doing my work, but what we've got is, in mathematical terms, we have two similar triangles. And what we mean by similar is they have all the same angles. So this is one of the triangles, this is the other one. These two triangles have all the same angles. They are similar triangles, which means that, and I mentioned it, but I didn't label it, this angle here is theta, okay? And so I can go through and I can, when I do the trig functions, I can look at both of them simultaneously. So that's important because now I can do 0.8 times ft for fty, and I get 0.8 ft equals 1.8. And because I've done all that, now I can solve for ft. Okay. So if I just continue to solve for ft here, let's see, ft equals 2.25 newtons. Okay. So there is ft. 2.25 newtons. Now that I know that, I can come back up here to my x equation. And I'm going to do this in a different color now. So I'm going to have ftx has to equal fe. Okay. ftx, so for that, I'm going to use the sine function, okay? And so that means sine of theta is going to be the opposite, which is 3 over 5. That has to equal ftx over ft. And so if I solve for that, that's 0.6 ft equals ftx. So this is 0.6 times ft. Fe is K, so I'm just using Coulomb's law now for the electrostatic force, so that's K, Q1 times Q2, but Q1 and Q2 are the same, so I can just put Q squared, because Q1 times Q2 is just going to give me Q squared over R squared. Okay, so continuing on, I know what Ft is. That's 2.25. I know K, that's 9 times 10 to the 9th, Q squared. R is the distance between the centers of my two objects, so that's going to be the 3 centimeters. That's right down here. That's going to be the 3 centimeters. So I need to convert to meters, so 0.03. Now, you may wonder, why am I converting to meters here when I didn't convert before? And by before, I mean right up here when I was doing the sine function and down here when I was doing the cosine function. So I didn't have to convert in these two cases because even if I converted to meters, it would have been like up here would have been 0.03 divided by 0.05, which is still 0.6. It wouldn't have changed this answer at all. And the same goes for down here. Because it's a length over a length, as long as they're in the same units, I get the same answer. Here, though, it has to be in meters because K is in terms of meters. We're using MKS units, so our constants are in MKS units, which means if we're using those constants, then guess what? Everything else has to be in MKS units. So that's why that has to be 0.03 there. Okay, so now it's just a matter of solving for Q squared. Okay. And so I do 0.6 times 2.25, and then I got to multiply by 0.03 squared and divide by 99. And I get 1.35 times 10 to the negative 13th equals Q squared. And of course, take the square root. 3.674 times 10 to the negative 7th coulombs equals Q. And there you have it. I have determined the charge magnitude and I've determined the tension. And I did this by using Newton's second law, doing the force diagram, and then setting up Newton's second law both for the horizontal forces and the vertical forces, using my knowledge of the individual forces, in this case the formulas, both there and here. I also had to use trig relationships, or vector analysis, and of course the given information I was told the normal force, as well as these distances. But the general approach is using Newton's second law and then using this new information we have specifically with regards to the electrostatic force.